Welcome back. Let us continue the discussion on the chemical kinetics, and here now we have looked at how the elementary reactions are involved in the production of multiple species or the intermediate radicals, and intermediate radicals are quite important to reaction to move forward. And also, while talking about the intermediate radical, we have discussed about chain reactions where the chain initiation takes place, then there is the chain propagation where the free radicals are produced, and finally the chain termination process you get to the stable product. And using the concept of steady state approximation, we can find out the rate coefficients and the production rate, all these things. Now, we are all ready to look at how we can now find out the chemical time scale. So, let us see how we calculate the chemical time scale. So, this is one of the important thing that requires, because most of the reacting systems they are exposed to fluid dynamical behavior and flow scale, time scale and other phenomena. Also, the magnitude of the time scale relative to the convective or mixing time scale is of importance in combustion, because when these reacting systems are involved, there are flow time scale flow time scale, there would be mixing time scale, there would be, if it is a multi-phase flow, there would be evaporation time scale, there would be other time scale if it is a radiation effect and other things. So, that is why the reaction time scale is of really of important in that sense. Now, let us start with the simple one with a unimolecular reaction. So, if we start with a unimolecular reaction, that is A goes to, so we stick to our nomenclature and continue the notation similar fashion. So, this is our, now this is what we already seen in 2.53, and this rate was products by dt, which is Kf to A. This is what we have seen in 2.54. So, these are already for a unimolecular system we have seen this. Now, what you can do, you can integrate this for a constant t, and for assuming A at T0 is concentration A at naught. Now, we integrate to find out what happens. So, then the concentration at any time t would be A naught exponential k t. So, this is our, now the characteristic time scale can be defined as the time required for the concentration of A to fall from its initial value to a value equal to 1 by E times the initial value. So, that means what we say A to A by ratio will go when this is 1 by E. So, this is what the characteristics time scale. Now, once we combine these two, 2.67 and 2.68, what we get is that, so you are now combining equation 2.67 and 2.68. So, what we get, 1 by E equals to exponential minus Kf tau chem, which is 2.69, or tau chem is 1 by Kf, which is 2.70. So, this is what one can estimate for a unimolecular reaction, the chemical time scale for that unimolecular reaction. Now, we look at what happens for a bimolecular reaction. So, here we got an A plus B forms C plus D. This is what we have taken earlier, and that would be K bimolecular coefficient. So, if you try to find out dA by dt, it will be K bimolecular A and B, which is 2.9. So, this is already for a bimolecular reaction, we have seen it. Now, for this single reaction A and B are related to stoichiometry. So, any change in A has a corresponding change in B. Now, you defined that way A naught, that should be corresponding change in B. So, which will let you to have A plus B naught minus A naught. Now, we substitute equation 4.71 into 4.9 and integrate then we get concentration of A at time and B at time equals to A naught by B naught exponential A naught minus B naught K bimolecular T. So, you get an exponential expression for the same thing, including your A and B. Now, again we do the same thing. Now, we got 2.72 and 73. Now, we substitute 2.72 into 2.73. So, what you get is 1 by E when T is tau chem, which means it will allow you to have tau chem equals to ln E plus 1 minus E A naught by B naught minus A naught K bimolecular. So, for a bimolecular reaction you get an expression for the chemical time scale. Now, if the concentration is quite high for B, then this tau chem will be 1 by B naught K bimolecular. So, it is a simplification. If the concentration is too high, then essentially this term goes to 0. So, it will become 1 by K bimolecular. So, this what you get an simplified expression for a particular system in a bimolecular system. Now, the last one is the trimolecular system. So, that what happens to the trimolecular system. So, we have taken a example A plus B plus M to K terminal C plus M, which will be. So, this is what we have previously defined. Now, for simple system at constant T, concentration of M is constant. So, in that case we got dA by dt equals to minus K M A B. This is also you have obtained. Now, this term K plays the same role as K bimolecular here. So, this is the term, if you look at it carefully, this is the complete term plays an. So, this sort of an equivalency one can think about K bimolecular. So, the effect is similar to that. So, then the characteristics time scale for the time molecular system one can estimate as ln E plus 1 minus E A naught divided by B naught. Here B naught minus A naught, which is K term into M. So, this is exactly where the equivalency with the K bimolecular. So, using the equivalency with the bimolecular system, we can find out that. Now, similarly, if the concentration of B is quite high, so this time scale would be 1 by B naught K tar into M. So, that is a simplified expression for that system. Now, this is what happens when basically you look at these different kinetics, and whole idea is that you can find out these characteristics time scale is the chemical time scale. Now, we move to a third one is the combustion chemistry. Now, this is an important again aspect, and what we are discussing now is these are all very important aspect of the fundamental of combustion process. Once we know these things, that will become the building block for our turbulent combustion. Now, for many kinetically controlled system, the number of elementary reaction step is quite high. So, that simple analytical explanation, that means when you look at even for example, the combustion of CH4, it goes through few hundred elementary steps. If you are interested, you can go to an website called GRI Make, which is from the Berkeley group, University of Berkeley, California. You can see there are different GRI mechanism version. The latest one is GRI 3, which is for methane combustion, and you can see there are multiple reaction steps. So, it becomes quite large number of steps where the analytical solution is not possible to find out chemical time scale. So, and top of that, not only the elementary steps, you have large number of chemical species which are also involved. So, that means one hand you have large number of reaction steps, then you have large number of species. So, in totality that becomes quite cumbersome to find out the analytical expression for chemical time scale. Now, even if it is for simple hydrocarbon, as I mentioned that CH4, these are informant are quite high. So, how the fundamental principle of chemical kinetics apply to this, we will consider some example here. Now, let us start with an example of the hydrogen oxygen reaction. So, this particular reaction is the global reaction or overall reaction, and but if you look at the elementary step, it could have multiple species, major species, and there would be some reaction step, and overall this reaction is exothermic reaction, where gaseous hydrogen and oxygen are quite stable at atmospheric condition. So, any conceivable direct reaction between two gases is not possible. So, the reaction half time at atmospheric condition has been estimated to be much larger than the age of the universe, which says that if the reaction is initiated by some free radical species, then the reaction proceeds very rapidly and violently. So, this is one of the important where these elementary reaction become important, where you get these free radicals, because any free radical they are quite reactive in nature. So, as soon as they are formed, they would be having a tendency to go towards some stable product and try to react with that and then form more radicals or some other product. So, that is where the elementary step reactions are important, where the free radicals will form and they will allow the reaction to move further. And this particular hydrogen oxygen case, there could be H, O, OH, these are the form. Now, we will consider this simplified mechanism that represent the hydrogen oxygen reaction at low pressure. So, the first step of the reaction. So, there would be these are chain reaction. So, first step towards the reaction is the initiation. So, what happens at the initiation stage, that hydrogen as a stable product, it gets into H radical, and oxygen as a stable product, it gets into O radical. Now, once that happens, so this is the initiation of the process. Now, my chain branching starts to take place. So, then O2 and H will combine to form OH and O, and H2 and O, so which are formed at the initiation stage, they will combine to form OH and H. Now, if you look at it in this process, again you get another free radical which is OH and this. Now, the propagation, now H2 will combine with OH and get H2 and H. So, these are the steps which will take place, and then finally the termination comes into the picture, where H to the wall it will terminate, or H with the oxygen will form HO2 and M. So, what happens that initiation step is the dissociation of some amount of molecular species by. So, when you look at this initiation step, to get this dissociation to take place, there would be some amount of spark or flame or something has to be provided which will dissociate these things. Now, once that happens, then you got the free radical, then free radical start. Now, there are some other energies which are associated with different bonds of these molecules like OO, HH, and they have different level of energies. Now, in reaction 2 which we are talking here, they are endothermic reaction by some amount. Reaction 3 and 1 are endothermic by some amount, and these reactions are relatively fast. So, you can also estimate from these bond energies and all these calculation that which reaction is quite fast and which is slow. Therefore, these OH and O radicals are the rapidly consumed, and the principal chain carriers remains as an H atom. So, which will tell you out of these radicals what you get in this process, which will be more reactive and which will stay there and allow to have. So, then you can find out the rate equation for this free radical density N star, which is taken as same as that H. So, your N star is here the H. So, that means we will find out dH by dt equals to K naught H2 minus K2 HO2 plus K3 OH2 plus K1 OH H2 minus K4 H K5 H O2 M. So, that is your. So, now other free radical species, like one can find out DOH also. Similarly, this would be K2 H O2 K3 OH2 minus K1 H2, which is your second step of the reaction. And for O, this will be dO by dt, which is O2 plus K2H O2 minus K3O H2, which is 3.3. since O and OH are both much lower than H, so that means O and both OH lower than H, we can assume that both of these species are at steady state. So, dO by dt, dOH by dt is 0, which yields that O at steady state is KO O2 plus K2 divided by K3 H2. So, that is what we get, and similarly for OH, OH at steady state is K2 HO2 plus K3 OH2 by K1 H2. Now, substituting this for O steady state, or we will use that O steady state that we got here, put there, we get 2 K2 H O2 plus K naught O2 divided by K1 H2. Now, we substitute the steady state value of OH and O radicals in the rate equation of the free radical density. That means d n star by dt, which n star is essentially here is H, which we have already looked at it. This is the n star here is. So, free radical density if we write, so that will be K naught H2, K2 H2 and K3. So, all these things we are basically it is a little bit of involved, nothing but the algebraic expression. So, all your OH and O steady state that we got, we will put it back there, and finally, you get in a simplified state of this steady state W naught F minus G n star. W naught is nothing but this expression, which will involve hydrogen and oxygen, F is this, G is this. So, that is where you get your the radicals, where F, if you look at here, that will be the chain branching, one can identify it that way. G would be chain termination. Now, if that is the situation, there would be two possibilities. Number one, G greater than F. So, that means the termination exceeds branching, or possibility 2, G is less than F. That means branching exceeds termination. So, the solution 1 or the possibilities 1 implies that. So, this will imply that K4 greater than 2 K2 minus K5 M O2. So, that G greater than F is assured at sufficiently low O2 pressure, and if we plot them with time, this is how your free radical density in this direction, and this is the time, and this is how this evolves, and this reaches an state where now solution will become then n star is W naught G minus F 1 minus e to the power t, which is 3.11. Now, at short times n star increases almost linearly with slope. So, with the slope of W naught t and reach it at a steady state value, which is W naught by G minus F. At higher oxygen pressure, at higher O2 pressure, G is less than F. So, then the solution remain N star is W naught by F minus G exponential F minus G T minus 1, which is 3.13, and if we plot that, this is how the free radical density that will evolve with the time. So, one case is higher pressure, another case is the lower pressure. So, we can see how that happens. Now, this case the free radical concentration increases exponentially, and since the overall rate depends on the radical concentration, the reaction velocity also increases rapidly. So, once this kind of situation happens, this is usually termed as explosion. So, that means it is a balance between radical concentration. Now, the hydrogen oxygen reaction behaves quite differently in different pressure regimes. So, that is there. So, you can possibly construct a explosion boundary for hydrogen oxygen reaction, and if you look at, there is total rate, different pressure, total pressure for hydrogen and oxygen. First regime could be slow reaction, second regime could be chain reaction explosion, third would be atmospheric flame thermal explosion. So, in step 1, here the reaction is wall recombination limited and proceeds to a steady state. Second stage, F here F begins to exceed G. So, the branch chain reaction. So, at region 1, that is in region 2, F begins to exceed G and branch reaction takes over, explosion issues. Now, in the region 3, where you come to here, when the pressure is further increased, the explosion is quenched and another regime of steady state is occurred. So, at this stage, when the explosion is quenched and another regime of steady state. So, in 3, kinetics are dominated by relatively unreactive H2 radicals. Other reactions in addition we considered above are important and also can be included. So, these are those steps which one can involve and see how many steps are there. Now, region 4 at a little high pressure. So, this is the region 4, the amount of heat liberated in the exothermic steps of the mechanism becomes larger than can be dissipated by conduction and other transport processes as the temperature rises. So, this in turn increases the rate of initiation and provides heats of endothermic chain branching reactions, leading to the net heat regime, which will lead to explosion. So, essentially this is the regime where it becomes quite. So, one can show these boundaries in a pressure temperature curve, where you have a slow reaction, ignition, this is the. So, this is your PT boundary of H2O2 reaction. So, that is a PT boundary. So, you can see different limits, first limit, second limit, third limit, and this side is slow reaction, this side is the ignition. So, this is how hydrogen oxygen reaction actually propagates. So, we will stop here and take it up in the next lecture.